So this is the nth term of a geometric sequence. We haven't quite started the Earth geometry topic yet. So there's your learning goal. Represent the nth term of a geometric sequence algebraically and determine the value of missing terms and position. So there's going to be a lot of variety to the types of questions that you might get, and you're going to have to be adaptable. So I'm going to teach you the common simple questions. I'll show you a couple of complex examples, but those complex examples can vary a lot. And doing some of the questions in the textbook will cover you off for that. I don't know what happened here, but something happened when I was writing recall, but anyway. Recall that a geometric sequence has a starting value and a common multiplier. We talked about this last lesson with the recursive definition of a geometric sequence. The starting value in this example is 2, and the common multiplier is 3. And that's the setup of our geometric sequence. Algebraically, we can write a geometric sequence like this. So the first term is T1, and we sometimes call it A. The second term is where we multiply the first term by R, and so we get AR. The third term is where we multiply the second term by R, we get AR squared. The fourth term, we multiply by again, we get AR cubed. The fifth term, AR to the power of 5. Now this is following the recursive definition. To get to the next term, I'm just multiplying the previous term by R. But hopefully you can see here that as we go along, we get an nth term. And what about the nth term? The nth term is AR to the power of n minus 1. And have a look at the pattern again. The second term was AR to the power of 1. The fifth term was AR, sorry, that should say 4. My apologies. AR to the power of 4. The fifth term was AR to the power of 4, so on and so forth. So that's our generalisation for the nth term. That's really the thing that you need to know from today. And the rest of today's lesson is going to be about just applying that knowledge. That's the nth term. That's also on your formula sheet. So here's an example. A geometric sequence has first term 4 and a common ratio of a half, the sixth term. Now, from last lesson, you could have done this. The first term is 4. And the common ratio is a half, so it goes 4, and then it halves to 2, halves to 1, halves to a half, halves to a quarter, and halves to an eighth. So that is an eighth. You could have done that from last lesson. But now we've also got the nth term. The nth term is AR to the power of n minus 1. And in this case, A is equal to 4 because that's the fourth term. R is equal to a half, that's the common ratio. And n is equal to 6 because we want the sixth term. So T6 will equal 4 times a half to the power of 6 minus 1, which is 4 times a half to the power of 5 is 1 over 32, and that is equal to 1/8, which is what we got by using the recursive feature as well. Now, it took us maybe longer to do it using the nth term than just using the recursive definition, but if we were asked for the 100th term, the nth term will be much quicker. So that's our point there. So I'll just put down here, this is last lesson and now. 2. So in example 2, and at the moment we're just dealing with just examples that are theoretical, but there could be context as well. We're going to talk about context in the next lesson. Compound interest is a common one. Any context that involves growth and decay, but there won't be any earth geometry context in there. So a geometric sequence has term 4 equals 9 and term 10 equals 72. What is the value of T8? When I'm setting out these questions, particularly early on, when I haven't done many of them, I'm getting used to the topic, I might think about looking at this visually, and I'm going to do this visually now. And that is that I know the fourth term and I know the 10th term. So I'm going to put little blanks here for the terms I don't know. So it's at 4, 5, 6, 7, 8, 9, 10 is 72. So they're the terms I know, and they're the terms that I want. And in particular, I'm looking to get term 8. And I can see straight away that term 8 here is going to be maybe 50, maybe 60, something around that area. I've got a bit of an approximation for term 8. It is a geometric progression now, and that's exponential. So I'm expecting it to be a bit lower than I'd probably expect for an arithmetic. But I've got an idea, and I can start to play with this. I don't know the first term, and I don't know the common ratio though. So I'm going to have to use some mathematical rules, and the index laws are going to come into question like this. So there's a procedure here that will probably come up in either your IA3 or your external exam, or both. This procedure will be really important. So let's start with T4 is equal to 9, and we know that T4 is equal to AR to the power of 3 equals 9, and we'll call that equation 1. We also know that T10 is equal to 72, and so AR to the power of 9, because that's n minus 1, is equal to 72, and we'll call that equation 2. Now, you'll see here, it doesn't quite look like it, but in the past you've done some simultaneous equations work, and simultaneous equations involve two equations with two unknowns. And if you have a look at 1 and 2 there, we have two equations, and A and R are our two unknowns. But they're not the classic simultaneous equations, 2x and 3y and that kind of stuff. This is a little bit different, but there's a really simple way to solve them. So the process here, with any question like this, is to get the equation with the high power and divide it by the equation with the low power. So in this case, I'm going to do equation 2, and I'm going to divide it by equation 1. And equation 2 divided by equation 1 is going to look like this. AR to the power of 9 over AR cubed so the bell's going to be on the video now, that's good. AR to the power of 9 over AR cubed is going to equal 72 over 9. And this is going to serve the purpose of eliminating the variable A. And that means we'll have an equation with just R left, which is really important. So I cancel out the A's. I'm left with R to the power of 6 is equal to 72 over 9. 72 divided by 9 is 8. And R is equal to, you'll have your calculator the whole time, the 6th root of 8, which will come out on your calculator as either 1.414, or if you're lucky it might come out as root 2 and you can keep an exact value. Again, I recommend to you though, you keep 4 decimal places and leave your final answer as 2 decimal places. So you might maintain 4 decimal places, and I don't know what it is to 4 decimal places, and I don't have my calculator. Maybe somebody could quickly do that.
Yeah, it's 1.4142.
42? Yes, excellent. Okay, so let's go with that. That's our R value. Now we can put that back into equation number 1 to get our A value. AR cubed equals 9, is that A is equal to 9 divided by 1.4142 cubed, or root 2 cubed, which is 2 root 2, it's about 2.8. So can somebody calculate that for me? 9 divided by root 2 cubed. Is there? Oh, there is 2. How about my calculator? I should only have one in here. That's all right. Matt is on it. 3.16.
Wait, how many decimal places?
Oh, let's go 4 again because it's not the end of the question.
3.1821.
1821. Okay, so 3.1821 is our value for A, and therefore we have this. Tn is equal to 3.1821 times 1.4142 power of n minus 1, which means that T8 is equal to 3.1821 times 1.4142 to the power of 7. And so we can do that calculation now. Now there are exact values in play here, so you might get an answer that's very close, but because of rounding is not quite what you would expect, and that's fine. So I get this, 35.99989. And so I'm going to say that's equal to 36, and actually it is equal to 36. And this is really interesting. We've set this up deliberately again, and we saw a very similar example to this last lesson. But if you have a look at doing a double, so we multiply by r twice, r squared, 9 goes to 18, 18 goes to 36, and 36 doubles to 72, So each 2 terms, the value actually doubles. And the in-between terms are a little bit more abstract and complex, but we get a doubling sequence there seeded into the main sequence. So we're happy with 36. Any questions on that? Don't be afraid if you get a not nice R value or a not nice A value. Just remember that if you use 4 decimal places and then transfer to 2 decimal places at the end, you really won't lose accuracy. You'll have plenty of accuracy to play with. Here's another example. I might pause here and give you some time to have a play with some examples. So in this example, we're told the first term, we're told the third term. It's always important to start considering what you have. Term 1 is equal to 7, and term 3 is equal to 63. Now the terms are quite low in the sequence. So the first term we know, the third term is only 2 on, so we can probably logically work out our value for R.
Freezes.
Sorry?
The screen's on freeze.
Oh, yep, thanks. So we can probably logically work out the value for R. And in this case, I can see that 7 times what equals 63, and R is 3. I could set this out diagrammatically, and I get this, 7 something, 63. What number do I multiply by twice to get to 63? I can work out a logical foundation for this, do a calculation from that. But again, the technical approach, because I want you to see this twice, is that we have T1 equals A equals 7, T3 equals A R squared equals 63. We do equation number 2 divided by equation number 1, and that gives us R squared is equal to 9, R equals 3, and so our common ratio is 3, and our A is 7, which leaves Tn is equal to 7 times 3 to the power of n minus 1. So we've built our understanding of the nth term. Just quickly create some more space here. Now that we've got that, it says which term is 5,103. So to do this calculation, I'm going to put in, so that just moved, a 5,103 as my term and try and determine what the n value is. So I get 7 times 3 to the power of n minus 1. 5,103 divided by 7 is equal to 729. So I get 729 equals 3 to the power of n minus 1. And now I'm looking for 729 as 3 to the power of dot. So keep in mind, particularly if you hung around in methods for a while, there are some logarithm rules that you could use to work this out, but you don't need to know logarithms in general maths. So you might get a question like this, and it would come down to, and I hate to say the word, but it will come down a little bit to trial and error. But it doesn't really have to be trial and error. All you have to do is sit and 3 to the power of what equals 729, and it will work out. So I'm going to go through and just do 3 times 3. That's 3 squared is 9. Multiply by answer by 3. Now I've got 3 cubed is 27. Press enter. 3 to the power of 4 is 81. 3 to the power of 5 is 243. 3 to the power of 6 is 729. So I get 3 to the power of 6 equals 3 to the power of n minus 1, which means that n minus 1 equals 6 and n is equal to 7. So this question is more complex. It's taking that next step with this question style, and you have to do a little bit of work to find a further value on. Now this is technical, and that would be a really good way of setting it out. Not a major problem though, if you just sit and go, I can't do that. And 7 times 3 is 21, times 3 is 63, times 3 is 189, times ... and you get up to this 7th term, and it's 5,103. You've got a calculator, you could do that as well. Part B says, when is it first over 1,000,000? This is a bit trickier. So 1,000,000 equals 7 times 3 to the power of n minus 1. Playing around with the sequence in full is a bit of a waste of time, and 1,000,000 is going to be a number that doesn't actually exist in our sequence. So there'll be a term n, like maybe term 10 will be a little bit less than 1,000,000, and then term 11 will be a little bit more than 1,000,000, and we want the answer therefore to be 11. So we need to find that point. Which one crosses over the 1,000,000 boundary? None of them will equal 1,000,000. And a good mathematician like this, even though you're using any of those skills like logarithms, will start by simplifying the equation as much as possible and then using a trial and error approach. So I'm going to start by dividing by 7 on both sides, and that gives me 3 to the power of n minus 1 equals 1,000,000 over 7, and that's the number I'm going to have in the calculator. That's the number I'm aiming for. And 1,000,000 divided by 7, 142857, that's what you're saying? 142,857.143 or something like that. We just want to see, when does 3 to the power of something get over that? So I'm going to go back to multiplying my answer by 3 and see what I get to. 729 was 3 to the power of 6. So 3 to the power of 7 is equal to 2,187. 8 is 6,000 something. 9 is 19,000 something. 10 is 59,000. 11 is 170,000. So we get this. 3 to the power of 10 equals 59,049. 3 to the power of 11 equals 177,047. And therefore, n minus 1 equals 11 is the first time over 1,000,000. And that means that n is equal to 12 is our answer. And you can verify this really easily. 7 times 3 to the power of 11 should be under 1,000,000. N minus 1, sorry. 7 times 3 to the power of 11 is 12 minus 1. That's over 1,000,000. And 7 times 3 to the power of 10 should be under 1,000,000. My apologies. 400,000. So you can verify your answer quite easily as well. Equals 12. The 12th term is the first time we're over 1,000,000. Any questions on that? Okay, we're going to just talk about our last little section, and then I'll give you the rest of the lesson just to get some work done and catch me up on your homework. Sketching geometric sequences. And we've talked about doing this recursively. It's no different to that. And if you can sketch or plot the first 5 or 6 or 7 terms, you'll be able to plot the associated exponential function without too much of an issue. So my example is, sketch the graph of Tn was 2 times 3 to the power of n minus 1, and the second one is 10 times a half to the power of n minus 1. And so I'm just going to go through and find my first 5 terms and sketch from those. So the first one is number 1 here. 2 times 3 to the power of n minus 1. The first term is 2. The second term is 2 times 3 is 6. And then 18, 54, and then 162. And sketching that on here, well, I won't do it yet because I'm going to do them both on the same axes. So the second one starts at 10, and then it's 5, 2.5, 1.25, and 0.625. Each of those terms I'm halving each time. So they're my 3 values, my 5 values. And now I'm going to plot it. You'll notice I put some notes over the side in purple. The notes say things like, plan your sketch. Don't be the person who gets into an exam where we've given you a grid that's the right size and you use a quarter of the grid, or worse yet, where you put your data points on the grid like this, and you've got 1, 2, 3, 4, and the 5th one has to be up here and you're working for the previous question. So make sure you plan your grid size and your scale. So I now know that my scale goes from 0 to 162 and from 1 to 0. So I need to go up to 162. And I know my x scale has to go to 5. So I'm going to set that up now. I've got 0 to 5, 162, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10. So I'm going to have 20s. So I've got 20, 40, 60, 80, 100, 20, 140, 160. So there's 160, there's 100. And I don't need a lot of data points on the scale. I don't have to sit there and fill out every one of them. That's a waste of time. As long as there's enough to the scale, we're good. So the first term was 2, which is smallest down here. The second term was 6, which is still quite small. The third term is 18, which is almost 20. And then the next one is 54, which is halfway between 40 and 60. And the next one is 162, which is right up here. And so our first sequence looks like this. That's the exponential shape, but keep in mind that this is, and I spoke about this in a previous lesson, it doesn't really make sense to connect our data points. So I've connected them so you can see the exponential shape, but in an exam, you leave them disconnected. The second one starts at 10, which is here, and it's not going to be a great scale for this one, and it halves each time. Like that. It has a similar shape, it curves down like that, but the scale's a little bit out. We've done that. I should take this off, and I will. And then, what do you notice? Hopefully you notice that for the sequence here, R, our common ratio is greater than 1, and it's a growth sequence. And for the sequence here, R is less than 1, and it's a decay sequence. It's going down towards 0. And they're the main features of our exponential growth graphs. We'll leave it there. Next lesson, we'll be moving on to Earth geometry.